Let's review oxidative phosphorylation and the electron transport chain, and then go through some practice problems about what happens when you have various perturbations, things like uncoupling agents, and you're running low on oxygen, you have too much protons, all these various scenarios. Let's start by just reviewing the electron transport chain and its importance and kind of how it allows us to power the synthesis of ATP. Its power is coming from redox reactions, favorable redox reactions, oxidation and reduction. Remember, your oil rig, oxidation is loss of electrons and reduction is gain of electrons. We have this value called the reduction potential that tells us how much a molecule wants electrons. So reduction is gain of electrons, reduction potential is its potential to gain electrons. And you release energy, you're energetically favorable, you've got a negative delta G. If you are passing electrons from something with a lower reduction potential, and by lower we mean less positive, to something with a higher reduction potential. So it's got a more positive reduction potential. Doing so is going to release energy. The bigger the difference in energy between the donor and the acceptor, the more energy is going to be given off. Through the breakdown of various fuels and catabolic reactions, you have these breakdown of molecules that are associated with the passing of electrons onto carriers like NAD plus and FAD. And those are going to then take those electrons to the electron transport chain. Then you're going to get a passing off of those electrons through various complexes. Some of these are going to be associated with the pumping of protons. You're going to pump protons into an intermembrane space, creating a gradient of protons that they're then going to use to power the synthesis of ATP. And so let's look through this pathway. We have our NADH, and our NADH is going to come in at complex 1. And our complex 1 is going to pump out pore protons, and it's going to pass the electrons from NADH through complex 1. So it's got like a series of carriers. It's going to pass it through complex 1 and onto Q. And as it does so, it's going to pump out 4 protons. When you pass the electrons to Q, you're ubiquinone, you become ubiquinol, QH2. That QH2 is now going to bypass complex 2. So you do not go from 1 to 2. You go from 1 to Q. And then QH2 is then going to take it to this complex 3. And so complex 3 is then going to pass those electrons to cytochrome C. And this is going to pump out 4 protons. Cytochrome C is this small protein, and it's going to take those electrons to complex 4. And in complex 4, you're going to pump out another 2 protons, and you're going to take the electrons and stick them onto oxygen, which is going to lead you to water. So oxygen is our terminal acceptor. And so oxygen is going to be our final acceptor of these electrons. If you can't pass electrons to oxygen, then the cytochrome C can't pass electrons to complex 4. And if it's held onto its electrons, it can't take any more from QH2. And if QH2 can't take any more, then NADH can't put it through this complex 1 in order to give you QH2. So if you don't have oxygen, we'll see that you're going to hold up this entire process. You need your terminal acceptor. So in our case of our NADH, we were pumping out 4 protons in complex 1. We were pumping out 4 protons in complex 2. And we were pumping out 2 protons in complex 4. And we were coming in with this complex 1 and passing to Q. Remember Q, we kind of have this Q pool. This Q is this small molecule that can diffuse through this membrane. And so it can pick up electrons from various places. It can pick up electrons through complex 1, but it can also pick up electrons through complex 2. Complex 2 is where we see FAD come in. Complex 2 is our succinate dehydrogenase of our citric acid cycle. We pass those electrons from succinate to FAD, which is then going to give us FADH2, which passes them to Q, and so now you're getting electrons to Q. But unlike the case with our complex 1, we're not pumping any protons here. We are, however, getting the electrons to Q, which can then take them to complex 3. So let's think for a second about why we don't pump protons in the case of complex 2, but we do pump them in the case of our complex 1. Let's think back to what's the purpose of pumping these protons? The purpose of pumping these protons is to make this gradient that we're then going to be using to power the synthesis of ATP. We have to actively be pumping the protons because we want to make it so that we've got a gradient of protons that we can use to power the synthesis of the ATP. Think of a dam, you've got a lot of protons building up. You're going to let them through the ATP synthase to make ATP using the electrochemical gradient that you are creating. So you got to be pumping protons against the gradient. It's going to take energy. So we need to have enough energy in order to pump the protons. And we need to think about whether we have enough energy in the case of our NADH, and if we have enough energy in the case of our FADH too. So we need to think of the difference in potential between our NAD and our Q and our FAD and our Q. Now, FAD has a higher reduction potential than NAD+. What this means is that FAD wants electrons more than NAD wants them. So you're going to get less energy passing electrons from FADH2 to Q than you would from NAD+ to Q. However, if you have a fuel source and you break that down, you're going to get more energy breaking down from that fuel source to FAD than you would from that fuel source to NAD+. So you're often going to see that NAD is going to be used for doing things like going from a carbonyl to an alcohol group, whereas FAD is going to be used for making CC double bonds. So you get more energy initially, so you can do those harder redox reactions, but then you're left over with less energy when you go and pass to Q. So it's always the difference in reduction potentials that you need to think about. With our NADH, we're going to have enough of our energy left over to pass to Q, but with FAD, we don't. Crucially, however, we still have the same overall amount of energy going from our fuel source to our Q. We're just breaking it up in different ways. And so in the case of our FAD, we had to use some of it for other purposes than pumping protons, but we have more of it left for pumping protons in the case of our NAD. And now we go take them to the electron transport chain. So let's review this one more time. NADH comes and it passes electrons to Q in complex 1, pumps out 4 protons. That takes those electrons to Q. Q becomes QH2, takes them to complex 3. Complex 3 puts them onto cytochrome C. Cytochrome 3 is this small protein, and it's bound to this heme that's bound to iron and stuff. And what it's going to do is it's going to bind to those electrons. It does it one at a time, which is why it kind of seems really confusing. But it does it one at a time, and it takes it to complex 4. You pump out 4 protons at this complex 3. At complex 4, you're going to pass those electrons on to the oxygen to make water and pump out 2 more protons. In the case of doing this, you get pumped out 10 total protons. In the case of our FAD, if we're coming in at Q, basically, so there are different paths to passing electrons to Q. Complex 2 is just this common one because it's the citric acid cycle component, but there are other pathway components. There are other pathways that can put electrons onto Q, such as with fatty acid breakdown. But the key thing is that Q can get electrons from multiple sources, but in doing so, we're not going to be pumping protons unless we're coming in at complex 1. So we're going to not be getting these 4, so we're only going to be having 6 protons pumped. Let's think about how many protons we need per ATP. So it's going to take 3 protons to actually go through ATP synthase in order to make 1 ATP. But we say it costs 4 protons per ATP made because we need to use a 4th proton in order to bring in a new inorganic phosphate group. So this H2PO4, this is just, I abbreviate this PI, a lot of places indicate it PI, that's standing for inorganic phosphate, and it's just a free-floating phosphate group. We need that phosphate group in order to make ATP. So that was one of our reactants. So we have ADP and PI. These are both going to be reactants that we need in order to make ATP. So we need to bring one in, and we're going to spend a proton in order to do that. So we need 4 protons total. We're also then going to be swapping back out the ATP we made and bring in a new ADP, but that's not going to cost us a proton. We're just going to do that, and then so that we have more ADP. So overall, for each NADH that goes in, you get about 10 protons pumped out. You need 4 protons coming in for 1 ATP to be made. So you get about 2.5 ATP per NADH, 10 divided by 4. Whereas with FADH2, You only have about 6 protons pumped. 6 divided by 4 is about 1.5 ATP per FADH2. And I say about because it's not like there's this direct link between one and the other. Because the ATP synthesis is powered by the gradient, it's not directly tied to the NADH or tied to the FADH2. One of the easiest ways to see this is just by thinking about the many ways you can get electrons onto Q. But you can be adding these two other sources, but you can also be dissipating your gradient in other ways. Some of these are helpful, such as bringing in the protons through the phosphate translocase, but others are more dangerous, such as uncoupling agents. And so we'll go through those in a minute. Here's a blank version of the diagram where you can fill out yourself to kind of think through what is happening where in the pathway. And I will provide blank versions of these you can fill out yourself. Now let's go through some practice problems. Let's start by thinking about electron transport chains and reduction potential. So when we talk about the electron transport chain, like the electron transport chain, when we say like ETC, we're often referring to the mitochondrial electron transport chain, but you can make electron transport chains from any series of electron donors and acceptors. The key thing is you want to be able to order them and see which steps are going to give you more or less energy. So we want to order these molecules into an electron transport chain that's thermodynamically favorable. Let's start with that. So we're given that we have these 4 molecules, A through D, and we're given their standard reduction potentials. Remember, reduction is gain of electrons, and so reduction potential is how much you want electrons. The more positive the value is, the more you want them, and the less positive the value is, the less you want them. So positive versus negative is in reference to hydrogen. And what you want to look for is just the difference between values, basically. And so what you want to look at, the most positive is going to be the highest reduction potential. The least positive is going to be the lowest reduction potential. And so we want to start at the one with the lowest and go to the one with the highest. So the one that wants it the least to the one that wants it the most. Let's see the one with the wants it the least. So we want to look for the least positive, which is going to be our minus 0.9. So we're going to start at A. And then we're going to want to look for the next one, which would be our D. The next one, our C, and then finally our B. So we order from the lowest, the least positive, to the highest, the most positive reduction potential. Now it's asking us to circle or otherwise indicate which steps give us the most energy. Now, to think about how much energy is given off, we need to look at the difference in reduction potential in our pass-offs. So we can simply take the differences between these and do our little math. We can see that the pass from A to D is going to have the greatest difference, so we're going to release the most energy. So this has the greatest difference in reduction potential, our delta E naught, and that's going to thus release the most energy. So this is going to be our most favorable pass-off. Now let's think about the mitochondrial electron transport chain and think about what would happen if we perturbed it. So question A is asking us, which of these would increase the concentration of protons in the inner membrane space? So remember that the inner membrane space is where we're pumping the protons into, building up the gradient in the intermembrane space so that the protons gradient can be used to flow through the ATP synthase and power the production of ATP. If we were to increase the concentrations of protons in here, we'll look and see what would happen. But first, let's think about how we could increase the concentration of protons in here. So we're given 3 options to consider: adding an uncoupling agent, adding an ATP synthase inhibitor, and removing ADP. Let's take these one at a time. First off, what is an uncoupling agent? Remember that an uncoupling agent and uncoupling proteins are going to let protons flow through without going through ATP synthase. And remember, ATP synthase is our complex 5, which is where we're making ATP. And so an uncoupling agent is going to allow us to have protons take an alternative route. So an uncoupling protein, this is common in brown fat in babies, and it basically allows the protons to go through a channel protein, and you're dissipating the energy as heat so the babies can stay warm. There are also small molecule compounds, these uncouplers or uncoupling agents, such as DNP, 2,4-dinitrophenol, These are typically going to be weak acids that what they do is they can kind of sneak the protons back through the inner membrane space. So you have this molecule, this 2,4-DNP, and it's going to pick up a proton in the inner membrane space where the pH is below its pi, meaning that you have more protons than you would need for half of it to be protonated. So you have higher protons out here, so it picks up a proton. It then diffuses through the membrane. And now in the matrix, the pH is going to be higher. And so there's less protons available. It gives off a proton. And now you've moved a proton from the inner membrane space into the matrix. You've dissipated your gradient. So the uncoupler is going to allow that to happen. So if we're removing the protons from the inner membrane space, what's going to happen to the concentration of protons in the inner membrane space? It would go down. So adding an uncoupling agent would not increase the concentration of protons there, it would decrease them. It would be increasing them in the matrix. So basically you're having this alternative way those protons can get through. So you're decreasing the concentration of protons in this inner membrane space. Okay, what about an ATP synthase inhibitor? So we're inhibiting complex 5, and we can kind of couple this with the next one, removing ADP. And so removing ADP, well, ADP is going to be a reactant for ATP synthase. So if we inhibit ATP synthase, or if we remove its reactant, in both cases, we can't have this ATP synthase going. And the ATP synthase not going means that we're not going to be having those protons flow through ATP synthase. And if we don't have an alternative route, we don't have an uncoupling agent, what's going to happen is that the protons are going to build up in this inner membrane space. So the protons are going to build up in here because the pumps pumped out until they couldn't fight the gradients. And so you've got the protons out here building up and can't come through. So if the concentration of protons in the inner membrane space increases, now which of these statements are true? Our options are it becomes more or less favorable to make ATP through ATP synthase. It becomes harder or easier to pump protons into it through the ETC. And it becomes more or less favorable to pass electrons through the ETC. And it'll be more favorable to make ATP because you've got the larger gradient that's powering the making of ATP. But that larger gradient makes it harder to go the other way against the gradient. So it's harder to pump protons into the inner membrane space. And if it's harder to pump protons, it's harder to pass the electrons because the passing of electrons is directly tied to the pumping of the protons. So if you can't pass electrons, you can't pump protons. And if you can't pump protons, you can't pass electrons. And that just has to do with the biochemistry of how these things are linked up and what's happening inside of these proteins. So you need to be able to pass electrons in order to pump protons, and you need to be able to pump protons in order to pass electrons. So in this case, if we have the protons in the inner membrane space high, the concentration of that, then it's going to become more favorable to make ATP through ATP synthase, but it becomes harder to pump protons, and it becomes less favorable to pass electrons. So if we were to be able to artificially maintain the proton concentration in that inner membrane space at very high levels, we would have a decreased flow through the electron transport chain, an increase in our ATP synthesis, assuming that we didn't have those high levels because we were inhibiting ATP synthesis. We would have an increased NADH to NAD plus ratio, because remember that NADH can't pass electrons through complex 1 to Q if you don't have enough electrons to pass. Because remember that NADH isn't going to be able to pass electrons through complex 1 if complex 1 can't take electrons because it's backed up. And so one thing to get backed up is going to get backed up all the way so that NADH is going to increase. And we'll see later how this is going to inhibit our catabolic enzymes. And the energy required to pump out protons is going to increase. But we can keep making ATP assuming that we don't have an inhibitor, because this is helping us see that the ATP synthesis is not dependent on NADH or FAD directly, rather it's dependent on the gradient, not the source of the gradient. So we already discussed what an uncoupler was, but let's go and think through what would happen to electron transport chain and ATP synthesis in the presence of an uncoupler. Remember, the uncoupler was going to let those protons flow through the membrane without going through ATP synthase. So we would expect ATP synthesis to go down, but we would keep flowing through the electron transport chain. We probably increase our flow through the electron transport chain because we're making it easier to pump because we're lowering the gradient. That's going to make it so that we're using more of our NADH, so our NADH to NAD plus ratio is going to go down, and it's going to make it easier to pump out the protons. So we have that the protons are flowing through this alternative way. It's going to decrease the concentration of protons in this inner membrane space. That's going to make it so that we have less of a gradient that we're pushing against, we're pumping against. It's going to make it easier to pump protons, which is going to make it easier to pass electrons. But we're not going to have enough protons left over to power the ATP synthesis. So our ETC is flowing more easily, and more protons are being pumped, but those protons aren't being used to make ATP. You're using more of our NADH, however, and so your NADH to NAD plus ratio decreases, which is going to relieve the inhibition of catabolic enzymes, and it's going to inhibit anabolic enzymes. We'll talk more about that in upcoming lessons, so you don't need to worry about that now, but it is something that you should start thinking about. One thing you should also think about is, would the number of ATP produced per NAD or per FADH2 be different in the presence of an uncoupler? So would the same amount of NADH and the same amount of FADH2 give you a different amount of energy if you had an uncoupler present? And would it be less or more? So in this case, we would generate fewer ATP because not all the protons you pump will be going towards ATP synthesis. So it's become inefficient, basically. Fill out the following table to indicate the effects of various scenarios on flow through the electron transport chain, ATP synthesis, and the NADH to NAD plus ratio. And it's asking us about the situations of decreased oxygen, decreased ADP, increased NADH to NAD plus ratio, and decreased NADH to NAD plus ratio. So let's think about this one at a time, starting with decreased oxygen. Remember that oxygen was our terminal electron acceptor. And so what's going to happen is that if you can't pass electrons onto oxygen, cytochrome C is going to get backed up. You then can't pass the cytochrome C, so Q is going to get backed up. If you can't pass the Q, then complex 1 and complex 2 are going to get packed up. So your NADH is going to build up, and that is going to inhibit the catabolic enzymes. You're going to not have electron transport chain flow because you're backed up, you're stuck. If your electron transport chain isn't flowing, then you're not going to have ATP synthesis going. You will have the proton concentration in the inner membrane space decrease because the ETC stops flowing and thus stops pumping. So it's easier to pump, but you can't be doing the pass-offs to power the pumping. So low oxygen is going to make it so the electron transport chain can't run. If the electron transport chain can't run, NADH is going to build up, and that's going to inhibit the citric acid cycle, which was our main source of the NADH. And it's also going to inhibit some parts of glycolysis. So this pyruvate dehydrogenase complex and this pyruvate kinase are going to be inhibited by NADH, as well as citrate synthase and alpha-ketoglutarate dehydrogenase in our citric acid cycle. And so you don't want to keep doing that catabolism if you can't be using the NADH that you make. So you shut it down. That's an example of our feedback inhibition. On the other hand, if we have high NADH, well, now we've got more of our fuel. We're going to be pumping more protons. We're going to be having more protons to power more ATP synthesis. And if we have a lot of fuel, and this is working efficiently, we can generate a lot of ATP. Conversely, if we don't have NADH, we don't have fuel, we can't make that. So with our oxygen, decreased oxygen is going to lead to decreased flow through the electron transport chain, decreased the ATP synthesis, and an increased NADH to NAD plus ratio. What about decreased ADP? So if we don't have ADP, and the same thing if we don't have inorganic phosphate. So maybe we inhibit this phosphate translocase, we can't bring in the phosphate, then we can't have inorganic phosphate. We don't have a reactant. We don't have ADP, we don't have a reactant. And so what's going to happen is that we can't make the ATP if we don't have ADP. So we need ADP, we need inorganic phosphate in order to make ATP. If we remove the ADP, we can't make ATP. And this keeps us from making a bunch of ATP unless we have a bunch of ADP. So if all we have is ATP, we're not going to want to make more ATP. But ADP is kind of the used form of ATP. So if we're building up a lot of the used form, we want to make ATP. But if we don't have a lot of it used, then we're not going to keep making more ATP. So if you don't have ADP, you're not going to be making ATP. So that's kind of like the rationale for it. But bottom line is if you don't have your reactant, you can't make your product. And if you can't make your product, this ATP synthase can't run. If ATP synthase can't run, then the protons are going to build up. If the protons are building up, it makes it harder to pump protons. If the protons can't be pumped, electrons can't be passed. Your electron transport chain is going to stop. The pumping of the protons is going to stop. You're not going to be able to make ATP. You're going to build up your NADH, and you're going to have basically this backlog. This is then going to make it so that your buildup of NADH is going to inhibit catabolism. You're going to activate anabolism, and so you're going to start using the ATP, and that is then going to give you more ADP so the system can start running again, and you are using your energy effectively. So if we look at that diagram, let's look at what enzymes are actually inhibited by NADH, and thus would be affected by altered NADH+ ratio. I realize like this table is kind of stupid because I say the ones that are inhibited and then I say effective NADH. But basically pyruvate kinase of glycolysis and pyruvate dehydrogenase of the transition from glycolysis into the citric acid cycle. These are going to be inhibited by NADH. And then those are also going to be metabolically irreversible steps. And so you want to regulate them and only go and do this, or only kind of commit yourself to making NADH if you are actually going to want to be able to use it in the electron transport chain. And then you have citrate synthase and alpha-ketoglutarate glutarate dehydrogenase in your citric acid cycle that are going to be inhibited by NADH as well. And so you have your electron transport chain is regulated by oxygen and ADP. That's going to help control the NADH ratios to control whether or not which direction metabolic pathways run and stuff. Now we want to consider a reconstituted membrane system that mimics the structure of intact mitochondria in that the matrix and inner membrane space are completely intact. These membranes are formed with only complex 4 and complex 5, so remember that's our ATP synthase, and these components are in their normal orientation within the membrane. Electrons are provided into the system via soluble reduced cytochrome C, and oxygen is used as an electron acceptor. Would ATP synthesis occur? Okay, so we've got these two complexes, and we're saying that we're providing reduced cytochrome C. So we're providing cytochrome C with electrons, and then we have the oxygen. Could we make ATP? Yeah, we can pump electrons through complex 4. It just needs the electrons to be brought to it by cytochrome C, and we're saying we're giving you cytochrome C with electrons. And so we've got that, and we need oxygen, and we've got both those things. That'll allow us to pump protons, and we can pump protons to make ATP because we have complex 5 as well. So we won't be able to make as much ATP because we're only pumping 2 protons per cytochrome C that we have. We're missing all this upstream stuff, but we can still make ATP. Booyah!